Hello, everyone. Welcome back. So today we're going to continue our discussion on 3-4, and we're going to talk about a couple of types of problems pertaining to the linear factorization theorem. And the linear factorization theorem says that any polynomial of degree n can be written as a product of factors. So if you look at this slide right here, it says that any polynomial in standard form, a to the n, x to the n power, plus a to the n minus 1, x to the n minus 1, all the way down, can be written as a product of linear factors, where C1, C2, and so on are all factors of the polynomial. Now, let's see where this comes into play for us. So let's take a problem like this. F of x is equal to x cubed minus 2x squared minus 11x plus 12. Let's use a linear factorization theorem to rewrite this as a product of factors, okay? And I know that my zeros or my factors are -3, 1, and 4. Well, in this case, the leading coefficient, a to the n, is 1. So the linear factorization theorem says that I can write this polynomial f of x as a to the n, which in this case is 1, times x minus -3 times x minus 1 times x minus 4. So when my leading coefficient is 1, I don't have to write that. I don't write when my leading coefficient is 1. So x minus -3 becomes x plus 3. X minus 1 stays the way it is, and x minus 4 stays the way it is. So that's what the linear factorization theorem says, that if I know my zeros, I can rewrite the polynomial as a product of factors. So another way you can think of this is a way of factoring a polynomial. So remember back in the day, you were given a polynomial, say g of x equals x squared plus 8x plus 15. And when you were asked to factor this, you would say, okay, well, g of x can be written as x plus 3 times x plus 5, okay? So with quadratics, you say the linear factorization theorem is just called factoring. But for polynomials, we give it a fancy name, namely the linear factorization theorem. Now, let's take, for example, a situation like this. Okay, so let's say we have the polynomial 2x cubed minus 3x squared minus 11x plus 6. And I know my zeros are 1/2, -2, and 3. So how would I use the linear factorization theorem to factor this polynomial? Well, my leading coefficient is 2. So it says g of x can be written as the leading coefficient times x minus 1/2 times x plus 2, because minus a -2 is plus 2, and x minus 3, okay? Now you're going to say, well, can I distribute the 2 in any one of these factors? You're more than welcome to, or you can leave it like this. If you want to distribute the 2 in any one of these factors, you cannot distribute the 2 in all of them. You can only distribute it to one of these factors. You can say, okay, g of x is equal to 2x minus 1 times x plus 2 times x minus 3. Okay. So you can write it either way. It doesn't matter to me on the test whether you write it this way or you write it the second way, where you distribute the leading coefficient to one of those factors. Now, let's talk about a concept called an irreducible quadratic. So an irreducible quadratic is a quadratic that cannot be factored. So an example of an irreducible quadratic is x squared minus 4x plus 1. Okay. We can't factor this quadratic. There's no numbers that multiply to give me 1, but combine to give me -4. Now, another way you can determine if your quadratic is irreducible is to find the discriminant. Okay. So the discriminant in this case would be b squared minus 4ac. In this case, b is -4 squared minus 4 times a, which in this case is 1, times c. So this gives me 16 minus 4, which is 12. Now, if your discriminant is either negative, or if the discriminant is a non-perfect square quadratic, non-perfect square positive number, then your quadratic is irreducible. Okay. So if you cannot tell if a quadratic is an irreducible quadratic, find its discriminant. If the discriminant is a negative number or a non-perfect square positive number, then that quadratic is in fact irreducible. So how are we going to use this fact? So let's take, for example, a situation like this. I want you to rewrite this as a product of factors, okay? And make sure that the factors are, write them as linear factors or irreducible quadratics. Well, I'm given that the 0 is -1. Now, I know from my fundamental theorem of algebra that since the degree of this polynomial is 3, that means I have one of 3 situations. I have a situation where I have either 3 rational solutions, okay? I have a situation with 1 rational and 2 irrational solutions. Or I have a situation where I have 1 rational and 2 imaginary solutions. Now, I know that the only 0 that I was given is -1. And I do not know what my other zeros are. I don't know if they all 3 are -1, or if they are just -1 is just one, the only rational 0 in this polynomial. So it is possible that I have a situation where all my rational zeros are all -1. That I have a solution -1 with a multiplicity of 3. That means that all 3 rational numbers are -1. However, it might be the case where the only rational 0 is -1. So how do I determine where to go from here? Well, remember, synthetic division tells me if I have a factor or not. And I know that since it's a 0, -1 is a factor of this polynomial, and that the quotient that I'll have left will be able to either be factored or not factored further. So I do synthetic division. Remember, when you do synthetic division, they have to be in descending order of power, and all powers must be represented. So I do synthetic division. And I get a 0 for my remainder, which I know because this was already told me already in the problem that this is a known 0 for this polynomial. Now, what is this quotient left? Well, since I started off with the cubic, that means these are the coefficients of my quadratic quotient. So the quadratic quotient is this. Now, can it be factored? Well, that's the next question. If it can be factored, that means I have more rational solutions. but since it cannot, so I need to know if I can factor this or not. Now I can sit there and say, okay, well, can I think of two numbers that multiply to give me 10, but combine to give me -6, or I can find the discriminant. So remember the formula for the discriminant is b squared minus 4ac. Well, in this case, b is -6. 4 times 1, a is 1, and c is 10. Okay, so 36 minus 40, which means my discriminant is -4. Well, if my discriminant is -4, that means that this is a irreducible quadratic. That means it can't be factored. So the only rational zero is this. Remember, what does a negative discriminant mean? That means that I have two imaginary solutions. So this is the situation with what I'm dealing with, that I have a polynomial with one rational solution and two imaginary. Do you remember why imaginaries and irrationals come in pairs? Okay. So if I had to factor this into linear factors and irreducible quadratics, then I'd say, okay, well, my only zero or my only factor, rational factor, is -1, so x minus -1. So that'd be my only linear factor. And the other thing that multiplies to this linear term is what I found my quotient to be, because it's an irreducible quadratic. So my answer would be x plus 1, because minus and negative gives me positive, times x squared minus 6x plus 10. So this is this polynomial factored into linear factors and irreducible quadratics. So take home point. When you find rational zeros, you plug them into you plug them in for C into this formula. And if you have imaginary or irrational, or if you have unfactorable quadratics, you just leave them the way that is. So this is this polynomial written as linear factors and irreducible quadratics. Now, most of the time, they will not give you the zeros like this, okay? So most of the time, they'll say, okay, well, here is a polynomial, x cubed plus x squared minus 4x minus 4. Rewrite this as a product of linear factors and irreducible quadratics. So what do I do? Well, first I need to find zeros. Well, I can use the rational root theorem and say, okay, well, first of all, before I even do the rational root theorem, we should see that if it's a cubic, that means what do I expect? Well, I either expect 3 rational roots or 1 rational and 2 irrational, or I expect 1 rational and 2 imaginary. Now, the 3 rational roots, it may be that all 3 rational numbers are the same number, or it can have a situation where all 3 are different rational numbers, or it can be a situation where I have 1 rational number with a multiplicity of 2 and another rational number with a multiplicity of 1. That means one of the zeros is repeated twice and the other zero is only repeated once. Or I might have a rational number that is repeated 3 times, or I might have 3 rational numbers only repeated once. So there's a whole host of possibilities with this option. And then these two are obviously if I have an irrational number or if I have an imaginary number. So how do I determine what are my zeros? Well, you use a graphing calculator or a graphing program. I like using this app called Desmos. It's spelled D-E-S-M-O-S. You can download it on your iPhone, iPad, or Android phone. And you can plug it in and plug in the equation and it'll tell you how the graph looks. Now remember, when we graph it, we are concerned with where this graph crosses the x-axis, because where it crosses the x-axis are my zeros. So if you look at the equation, x cubed plus x squared minus 4x minus 4, I see that it crosses at -2, -1, and 2. So that means my zeros are -2, -1, and 2. That means I have 3 rational zeros, all of which have a multiplicity of 1, or all of which are different. So -2, -1, and 2 are my zeros. So now that I know where it crosses, I can say, okay, well, I have a situation right here whose zeros are -2, -1, and 2. So now I'll plug it into the linear factorization theorem and says that I can rewrite this as x minus -2 times x minus -1 times x minus 2. Now it's just a matter of cleaning it up. X minus -2 is the same as x plus 2. X minus -1 is the same as x plus 1. And x minus 2, we don't have to clean it up. So this is the factored form of this polynomial. Okay. So let's look at another example. G of x equals x cubed minus 10x plus 12. Again, it's a cubic, so the same possibilities hold. 3 rationals, of which they can all 3 be different, or they can be repeated 2 times or 3 times. 1 rational and 2 imaginary, or 1 rational and 2 irrational. Remembering that imaginaries and irrationals come as sets. So I go to my graphing utility, and I see that this guy crosses the x-axis 3 times. But I can't really make out exactly where some of these things are. But I see that it definitely crosses at -2. So I know one of my rationals is -2. Now, what is the other rational? Well, I can't tell. I don't know. So since I only know -2 as one of my zeros, I can go back and use synthetic division. So I know one of my zeros is -2, and I use synthetic division. 1, 0, -10, -12. Why did I have to put a 0 there? Do you remember? It's because it's missing the x squared term. So remember, when I'm missing a power, I have to represent it with 0, okay? So do synthetic division. And I do in fact get 0, which I expected because I know it was a 0 or a root of this polynomial. Okay, so what does that mean? That means I can rewrite g of x as x minus -2, or x plus 2, times x squared minus 2x minus 6. Now, this is the place where things get kind of hairy. My question is, can this be further factored? Well, I can sit there and try to figure out whether there are numbers that are factors of 6 or multiply to give me 6, but add to give me -2. Or I can use the formula for the discriminant, looking for either a negative discriminant or a positive discriminant that is not a perfect square. Okay, so in this case, for this quadratic, b is -2, minus 4 times a, which is 1, times c, which is -6. So -2 squared is positive 4. Minus 4 times 1 times -6 is plus 24, which gives me a discriminant of 28. Now, it's positive, okay? Now, if it was a perfect square, remember perfect squares are numbers like 1, 4, 9, 16, 25, 36, 49, 81, etc. Numbers whose square root is a whole number. Or it's not a perfect square. So 28 is not a perfect square. So that means that this is all that x squared minus 2x minus 6 is an irreducible quadratic because it cannot be factored. Okay, so this is basically how we factor a polynomial. Okay, we break up the polynomial into linear factors, factors with rational number zeros, and if we have irrational or imaginary zeros, we keep them as quadratics that can't be factored or irreducible quadratics. All right, one more. H of x equals x cubed minus 5x squared plus 17x minus 13. Well, what do we do? Okay, so the first thing you should do is graph it. And we see that it crosses, in this case, the x-axis at 1. So I know that one of my roots is, or one of my zeros is 1. Okay, now, how do I find the potentially other factors? Okay, do synthetic division. 1, -5, 17, -13. Now, remember, I'm expecting that my remainder will be 0 because it's a factor. Okay, now, what does that mean? Well, I can rewrite h of x as a product of x minus 1 times x squared minus 4x plus 13. Now, can I further break down x squared minus 4x plus 13? Well, let's use the discriminant. Okay, the discriminant, b squared minus 4ac. So b in this case is -4 squared minus 4 times a, which is 1, times c, which is 13. Okay, now -4 squared is 16, minus 4 times 13 is 52, which gives me -36. So the discriminant is negative. That means I expect 2 imaginary solutions. And moreover, that means the quadratic is not factorable, so we keep this as an irreducible quadratic. Okay. Now, what if I asked you what are all my zeros, whether they are imaginary, irrational, or rational? Well, I know that my 1 0 from my graph is 1. And to find the other 0, how would I do that? Well, I have to solve the quadratic. And since we know it's not factorable, we use the quadratic formula. So -b, so -4 plus or minus the square root of the discriminant, which is in this case -36. All of that over 2 times a, which in this case a is 1. Okay. So minus -4 is +4, plus or minus, well, remember the square root of -36 is 6i. over 2. Now, remember how I simplified this fraction. I look for a common factor in both of my terms in the numerator. Both 4 and 6 have a common factor of 2. So I factor out the 2, and the 2 in the numerator and the 2 in the denominator cancel. So I can only cancel once I factor out from the numerator. So my solutions are x equals plus or minus 2, x equals 2 plus or minus 3i. So what are my zeros? Well, my zeros are 1, the one I found using the graph, 2 plus 3i, 2 minus 3i. Okay. So this is a situation where I'm expecting 3 zeros and I got a 1 rational and a pair of imaginaries. Now, an alternative way of using the linear factorization theorem. So what if I said I'm looking for a polynomial whose zeros are 3 and 1 minus root 2? So what do? How do I find a polynomial whose zeros are 3 and 1 minus root 2? Well, if 1 minus root 2 is a 0, then I know, because this is an irrational, that 1 plus root 2, its conjugate, is also a 0. So what would be the degree of the polynomial that has 3 zeros? Well, it has to be at least a degree 3 polynomial. So I know it's a degree 3 polynomial, or a cubic. Now, how do I use this to find the actual equation? Well, I know these are the zeros. The factors are x minus 3, x minus 1 minus root 2, and x minus 1 plus root 2. Okay. Now my job is to multiply this out. So when you have a situation like this, you want to multiply those factors with the imaginary or irrational roots first. So I'm going to first multiply these two guys. Okay, so remember, how do we do this? We FOIL, right? So first is x times x, which is x squared. Outside gives me x times negative, in parentheses, 1 plus root 2. So it gives me negative x times 1 plus root 2. And then inside, so this part times this. So that gives me negative x times 1 minus root 2. And then the last. So negative times negative is positive, so plus 1 plus root 2 times 1 minus root 2. Now, let's clean this up. So if I distribute, I get x, negative x, minus x root 2. Here I get negative x plus x root 2. Now, remember, this is a irrational number and its conjugate. So when I multiply a number by its conjugate, what do? Remember, this is a difference of squares. So remember, when you multiply a number, a binomial, by its conjugate, it's a difference of squares. So it's the first term squared minus the second term, which in this case is root 2 squared. So let's clean this up some more, okay? So negative x root 2 and positive x root 2, they cancel. And that's always should happen. Your root number, your variables multiplied to a root or to an imaginary number should always cancel, okay? And so I get x squared minus x is minus 2x plus 1 squared is 1 minus root 2 squared is 2. So 1 minus 2 is minus 1. So if this is just the product of x minus 1 minus root 2 and x minus 1 plus root 2. So x squared minus 2x minus 1 is what I get if I multiply these two guys. But I'm still not done. I still have to multiply this by x minus 3. Now remember, how do I multiply a binomial times a polynomial? I take every term in the binomial and multiply through by every term in the trinomial. So the first thing I'm going to do is distribute the x to every term in the trinomial. So x times x squared is x cubed. X times negative 2x is negative 2x squared. And x times negative 1 is negative x. And then I do it again with negative 3. Negative 3 times x squared is negative 3x squared. Negative 3 times negative 2x is positive 6x. And negative 3 times negative 1 is plus 3. Okay. Now I combine my like terms. So negative 2x squared minus 3x squared gives me negative 5x squared. Minus x plus 6x gives me plus 5x. And there's nothing to combine 3 with. So this is the cubic that, when factored, would give me the zeros 3, 1 minus root 2, and 1 plus root 2. All right, let's do one more. Let's find a polynomial whose zeros are negative 2 and, say, 2i. Okay. Well, if 2i is a 0, then I know its conjugate, negative 2i, must also be a 0. So plug it into my linear factorization theorem. X minus negative 2, which is x plus 2, x minus 2i, and x minus negative 2i, which is x plus 2i. Now I FOIL these two, and I get x squared. First, our x squared outside is plus 2ix. Inside is minus 2ix. And last is negative 4i squared. So remember, what is I? I is the square root of negative 1. So negative 2i times 2i is negative 4 times I squared. So 2ix minus 2ix cancels. It gives me x squared minus 4i squared. But remember, I squared is just the square root of negative 1 squared, which is negative 1. So this is x squared minus 4 times negative 1, which gives me x squared plus 4. So by foiling this, I get x squared plus 4. Now, I'm not done. I still have to multiply through by x plus 2. Okay, and again, I can FOIL. So the first terms, x times x squared is x cubed. Outside is 4 times x, which is 4x. Inside is 2 times x squared, which is 2x squared. And last is 2 times 4, which is 8. Now, for completeness sakes, write them in descending order of power. There we go. Okay. What if I had a problem like this? What if I'm looking for a polynomial whose known zeros are -1 and 2 minus 2i? Well, if 2 minus 2i is a 0, then 2 plus 2i is a 0. Now I put this into my linear factorization theorem. So x minus -1, which is x plus 1, times x minus 2 minus 2i times x minus 2 plus 2i. Now, some of you will be tempted to distribute the negative here or distribute the negatives here. I highly advise not doing that because it's going to make your polynomial a lot more complicated. So just do minus the entire root in parentheses. Do not distribute the negative through now. Okay. So we're going to start off by multiplying my factors with my imaginary roots. So x minus 2 minus 2i times x minus 2 plus 2i. And when I do the math, I get x squared minus x times 2 plus 2i minus x times 2 minus 2i and plus, because this negative times this negative is going to be plus 2 minus 2i times 2 plus 2i. Did you get to this step? If not, you need to ask me where I can help you get to this level, okay? If you didn't, make sure you pay attention to your foiling and feel free to contact me or talk to me during our normal group sessions. Okay, so let's clean this up. We can distribute the x. And remember, what do we do here? This is a binomial times its conjugate, so it's a difference of squares. Okay, so the minus ix and plus ix cancels out, which should happen all the time. So x squared minus 2x is minus 4x. 2 squared is plus 2 squared, which is 4, minus 2i times 2i. So remember how do we do 2i squared? It's 2i times 2i, which is 4i squared. And remember, I squared is -1. This is equal to -4. So minus -4. minus 2y squared, but in this case, 2y squared is negative 4. So this gives me x squared minus 4x plus 4 plus 4, which is x squared minus 4x plus 8. So this whole thing is x squared minus 4x plus 8. Now, that's just the multiplication of these two binomials, okay? I still got to distribute through with x plus 1. So this is an example of an irreducible quadratic, because this quadratic, if you solved it, you would have gotten the roots 2 minus 2i and 2 plus 2i. So now we distribute the x first. So you get x cubed minus 4x squared plus 8x. Then we distribute the 1. So we get plus x squared minus 4x plus 8. Combine like terms whenever possible. X cubed minus 4x squared plus x squared gives me minus 3x squared. 8x minus 4x is plus 4x plus 8. Right, hope this video was helpful, and I will be anticipating any questions that you may have. Remember you can email me or message me as you encounter any difficulties, and I will respond as soon as I can. If you need some private sessions, video conferencing sessions, let me know. Otherwise, make sure you have questions formulated for our next group meet. And I will see you on the next video. Thank you.